A GCN weights neighbors by graph structure, not relevance. PyTorch Geometric's GATConv learns edge attention, so the node classifier can focus on the neighbors that actually matter. You'll see how to connect the pieces into a workflow that labels nodes and shows which neighbors mattered most. I'm Professor Pi, teaching AI foundations with simple Python. Graph attention is a practical fix for a common pain. Some neighbors help a prediction, others just add noise. A standard GCN mixes neighbors with a fixed normalization, which can blur an important signal. GATs let the model pick which edges to trust. PyTorch Geometric packages that into compact layers so you can experiment without hand-building sparse algebra. At a high level, attention scores every incoming edge and uses those scores to mix neighbor features. Think of a citation network. One cited paper might be highly relevant, while 3 others are peripheral. Attention boosts the useful citation and downweights the rest. The upside is interpretability and flexible weighting. The trade-off is extra parameters and more memory when you add many heads. We will build a tiny toy graph, inspect raw attention, wrap that into a small classifier, and finally train the same pattern on the Cora citation dataset to see actual neighbors that matter. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. The first snippet builds the smallest graph we need, so the question is visible before any learning. This snippet builds the smallest PyTorch geometric graph we need for attention. A GCN-style update would treat the visible incoming edges as structure first, then mix neighbors by a fixed normalization rule. Here, data holds X for node features, edge index for directed message flow, and Y for later node labels. The edge index layout makes node 0 receive messages from nodes 1, 2, and 3. So the graph already contains the exact question we care about: which neighbor should matter most? The output confirms the graph size before we add any model behavior. Now that we have a minimal graph, we need to see how a GAT layer turns node features into learned embeddings. This snippet applies PyTorch Geometric GATConv to turn each node into a learned embedding. The key move is heads equals 2 with concat true, which means each head produces its own 3-value view, and GATConv concatenates them. That is why node 0 ends up with width 6 instead of width 3. The dropout equals 0.0 setting keeps this first pass deterministic, which is useful while learning the mechanics. Increasing heads gives the layer more separate attention channels, but concat true also increases the next layer's input width and memory use. The output shows the visible effect of multi-head attention on one node's representation. Raw embeddings are useful, but to debug what the layer attends to, we must expose the attention coefficients directly. The next snippet shows how to inspect them. This example uses PyTorch Geometric GATConv with return attention weights equal true to expose the attention table. The temporary zeroing makes the coefficients tied, which is a teaching simplification, so the inspection code is easy to trust before training changes the values. GATConv returns H plus at edge and alpha, where at edge stores source and target node IDs, and alpha stores per head coefficients. The mask keeps only edges whose target is node 0, then score averages across heads and selects the highest entry. The output shows which incoming source is selected by the inspection pipeline, setting up the same check after learning. Embedding inspection is good, but we want a compact classifier that trains end-to-end and also yields attention for debugging. We adjust aggregation so the classifier head stays small. This snippet turns GATConv into a reusable PyTorch geometric classifier shape. The concern now is not just producing embeddings, but producing one logic vector per node that can plug into cross-entropy. GATnet.forward returns normal class logits, while GATnet.attend makes a separate call with return attention weights equals true for later debugging. The important tweak is concat false. The 4 heads are averaged instead of concatenated, so the output width stays equal to outch. That keeps the classifier head compact and avoids an extra projection layer in this small baseline. The output confirms that each node now receives 2 class scores. With the classifier in place, we can train on a real dataset and reuse the same inspection flow to answer which neighbor mattered most for a prediction. This snippet turns GATConv into a reusable PyTorch geometric classifier shape. The concern now is not just producing embeddings, but producing one logic vector per node that can plug into cross-entropy. GATnet.forward returns normal class logits, while GATnet.attend makes a separate call with return attention weights equals true for later debugging. The important tweak is concat equals false. The 4 heads are averaged instead of concatenated, so the output width stays equal to outchar. That keeps the classifier head compact and avoids an extra projection layer in this small baseline. The output confirms that each node now receives 2 class scores. This snippet trains a compact PyTorch geometric GAT baseline on the Cora node classification dataset. Planetoid loads one graph with features, labels, and train mask, so the loop can optimize only the labeled training nodes. Net data produces logits for every node. F.crossentropy scores the training slice, and Atom updates the GATConv attention and projection parameters together. After training, net.attend data returns edges and weights, letting us reuse the same ranking pattern from the toy graph on a real citation network. The output shows node 0's predicted class and the neighbor with the strongest averaged attention into that update. Mapping this back to a real project is straightforward. Swap Cora for your own small citation or interaction graph, and keep the same inspect and audit path to see which neighbors drive a node label. For larger graphs, you'll need batch or neighborhood sampling, but the attention interpretation, who influenced the update, stays the same. Quick summary. A graph attention network learns per edge weights, so node updates can focus on informative neighbors. Use it when neighbor relevance varies and when interpretability matters, for example in citation networks or molecule graphs. One caveat: multi-head attention increases memory and parameter cost, so monitor head count and concat mode. A concrete next step: on the Cora baseline, try increasing heads from 2 to 4 while switching concat from true to false. Then compare validation accuracy and inspect how the top neighbor rankings change. That single change often reveals whether more attention channels help or just add noise. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.